This is the second example on related rates, and this time a spherical balloon is being inflated at a rate of 20 cubic feet per minute. Find the rate at which the surface area of the balloon is increasing when the radius is 6 feet. So this one, again, we're going to start the same way by defining the variables. And what we've got initially is a little bit unclear, because it says a spherical balloon has been inflated at a rate of 20 cubic feet per minute. Well, what quantity is that? What do we call a quantity like that? It doesn't tell us. It doesn't tell us whether it's the radius or what it is. Well, the clue here is the cubic feet. Okay, so when you see cubic units of length, a foot is a length, and cubic units almost always indicate that we're talking about volume. Okay, so let V be the volume of the balloon. And it's a spherical balloon, so you might as well note that, because the volume of a sphere has a specific formula. Now, we're also asked to find the rate at which the surface area of the balloon. So surface area, so we'll just go with A again for surface area. Surface area of the balloon. Again, it's a sphere, but we've already pointed that out now at this point. And then we've also got the radius. So let R be the radius of the balloon. We'll make that a capital V for volume. Okay, so now we've got to write down the given information, the given rate, as a derivative. Okay, well, if V, the volume, is changing at 20 cubic feet per minute, if V stands for the volume, then the rate of change of the volume, how quickly it's changing, is dV dt. Okay, so d dt, remember, tells you how quickly something is changing. So the volume is changing at a rate of 20 cubic feet per minute. The desired rate here is the rate at which the surface area of the balloon is changing. Well, if A stands for surface area, the rate at which that's changing, we're going to label that as dA dt. The derivative tells you the rate of change, so d dt. Okay. Now, the instructions you had previously were to look for a formula that relates the given rates and the desired rates, or at least the variables within these. Now, we don't have a simple equation that relates the volume of a balloon to the surface area of the balloon, but we do have formulas for each. Okay, so let's work with what we know. So let's say the volume of a sphere. That's V equals 4 over 3 pi r cubed, and A is equal to 4 pi r squared. That's the formula for the surface area of a sphere. Well, let's differentiate each of these. We know that differentiation is involved. We have dV dt and dA dt, so differentiate each of these with respect to time. So dV dt, right, this one multiplied by the 3, that will be 3 times 4 over 3. In other words, the 3's will cancel. So 4 pi r squared. And remember, since we're differentiating with respect to time, we need to make this dr dt. This is the new step that we talked about before. Whenever you differentiate a variable now, since you're differentiating with respect to time, you need to attach dA dt. We're going to want dA dt, so let's do that now to see what it looks like. dA dt, differentiate here, multiply them by the power, 2 times 4 is 8, pi is just a constant, so keep it there, 8 pi r, reduce the power by 1, and again, since we're differentiating with respect to time, don't forget to make this dr dt. Okay, so this step and this step This is the new stuff that you have to look out for all the time, okay? Well, let's see what we can do with this. Let's work with the dV/dt, because we know what that is. And we know that dV/dt is 20 cubic feet per minute, is equal to 4 pi, and we have differentiated now, so we can put in any variables that we know. And we were told, if we look back at the question, that the radius at this point is 6 feet. Okay, so we can put in the radius as 6 squared dr dt. Now the only unknown we have here is dr dt. So that's going to give you 20. 6 squared is 36. And 4 times pi times 36 dr dt. So if we want dr dt on its own, we can simply divide across, and you'll get 20 divided by 4 by pi by 36 is equal to dr dt. So that leaves us with 4 goes into 20 once, 4 goes into 25 times. So dr dt is equal to 5 over 36 pi, and this again is when r is equal to 6. Now, that's going to be useful to us. If I can control the surface for a moment. That's going to be useful for us because the only quantity that we didn't know on this equation was dr dt. Okay, so we can substitute that in there. We know r is 6, so we can go with this now. And we have dA dt is equal to 8 pi, r is 6, and dr dt is 5 over 36 pi. Now let's see what happens here. Immediately, the pi's will cancel. 6 goes into 6 once, and 6 goes into 36 6 times. Okay, and it's getting a little bit messy, I apologize for that, but that gives you dA dt is equal to 8 5s are 40 over 6, which is 6 and 4/6, or 6 and 2/3. Now, let's get our unit right. Okay, let's get our unit right. It was going to be its area, and the radius was measured in feet, so the area will be measured in feet squared, and we're differentiating with respect to time, so it'll be per minute. Time is measured in minutes in this question. So dA dt is equal to 6 and 2/3 squared feet per minute. Okay. So there isn't always a direct one-to-one link between the two quantities that you're interested in most, but there's always a way of getting there in the end. Okay.